quotas in OpenStack in general. So why this is important, and we'll just cover few basics and the current state of compute scheduling and quota in OpenStack, and even touch base on what in future we plan to do in these particular areas. So Nikhil, if you can move to the next slide. So a little bit of background about myself. I'm Vilobh. I'm an active contributor to OpenStack. I am a core contributor for Magnum. I work in the areas of, I contribute heavily in the areas of Magnum, which is container as a service, and Noah, which is compute as a service. I'm also, I've also introduced nested quota to Cinder and OpenStack in general. So I'm the first one to introduce nested quota in OpenStack in general. So working on the efforts to have a common library to, or a common entity to have quotas to have a common library for quotas, and working on all the efforts which will help us to have a common framework and every project can make use of it. So Nikhil, if you can move to the next slide, please. So today's agenda. So how scheduler works. So first of all, I'll go through how the scheduler works. Then next is resource tracker, how the resource tracker works. And then what is the significance of resource tracker in OpenStack or compute in general. Then next is how the scheduling, how the filter scheduler works and takes into consideration the filters and the weights associated with it. And then why do we need quota? What is the significance of using quota in OpenStack? What are the problems we will run into if the quota is not managed properly, and how things there can be problems if you're using scheduling at scale or like quota at scale, and then quota management in nested projects. So we'll go to the next slide. So how scheduler works. So first of all, like in any OpenStack deployment, we will have these 3 or 4 important processes. So conductor has been introduced since Juno, and most of the OpenStack deployments have conductor, but most predominantly any deployment has the Noah API, the Noah scheduler, and Noah compute. So by API, I mean the Noah API here. Conductor is Noah conductor, scheduler is Noah scheduler, and compute is Noah compute. So so depending on the deployment, all the 3 services, all the 3 processes, that is Noah API, Noah conductor, and scheduler, can run on the same API box, and compute can run on a compute box. So first of all, what happens when you try to boot a VM? So let's go from there and then understand the nitty-gritties of how the scheduler works. So whenever you try to boot a VM, the flow goes like the user request with, let's say, boot 1 instance, depending on like you can even specify X number of instances, X being like 2, 3, 10, or 100, but let's say we start with smaller. So boot an instance, the request goes from API to the conductor, and the request is saved. That is, conductor is the interface which will talk to the DB and which will save the request details, what has come in, and then the conductor will go and talk to the scheduler. So the scheduler is the person who is responsible for selecting which host your instance would be running on. So let's consider, in case of VMs, if you have a bunch of hypervisors, let's say your deployment has thousands and thousands of hypervisors, scheduler is the entity which is responsible for picking up a particular hypervisor depending on various criteria that it goes through. May it be the availability of physical resources like RAM, disk, CPU, and then picking up a compute, which is a hypervisor, and then giving the details to the conductor, and then the conductor in turn will communicate with the compute, and the compute will invoke the respective drivers. So let's say you're using libvirt, and it will spin up an instance. So scheduling becomes a critical part. It is more of a policy. It is more of a brain, more of logic, where it says that where your instance should be placed, or where which host will have your instance. So if we move to the next slide. So I hope this is clear. And so resource usage tracking. So why resource usage tracking is important? So first of all, resource tracker is an entity which runs inside Noah Compute, and it periodically runs, the periodic time being 60 seconds. It runs periodically to monitor and to grab usage of resources on a particular compute. So let's say what resource tracker does is it monitors how much CPU is available, how much memory is available, how much disk is available, and all other physical resources that are there, that a compute keeps track of. So right now, compute is very local, and it is very centric to whatever it can see locally on a particular hypervisor or compute. So I'll be using hypervisor or compute interchangeably. They mean the same thing, and at least in this context of compute scheduling. And Noah Compute is the one, or resource tracker running inside Noah Compute is the one who is responsible for getting a holistic view of what are the current usage patterns, or what is the current usage details on a particular hypervisor. So resource tracker runs periodically, which is 60 seconds, grabs these details, and it dumps these details in NoahDB, specifically in the compute nodes table in the NoahDB. And previously, before the introduction of conductor, it used to happen that Noah Compute used to directly talk to DB, but this can be prone to many security flaws and security issues. So as a result of which, the Noah conductor process was introduced, which now becomes a single point of contact for anything related to talking to DB. So now Noah Compute, as we can see here, that periodically on the right hand side, periodically updates the node resource within 60 seconds interval. So gets the hypervisor resource, consuming the resource, update to DB. So Noah Compute gets those details and talks to conductor, and the conductor will update the DB. So now let's go through the entire process again. So Noah API gets the request, that is whenever an admin or a user issues Noah boot, given a particular image, given a particular flavor, and the name of the instance, and let's say you right now just have a default availability zone, uh, then you boot an instance, the request goes to conductor, goes to scheduler. Scheduler will pick, let's say it picked a host depending on, let's say we just had 10 hosts, and out of that, host 7 had maximum amount of RAM free, and our criterias were like choose a host which has maximum RAM free. So scheduler picked a host, gave it, returned the host, and then the call went to that particular compute, and an instance was spawned there, and we got the instance up and running. Okay, next slide. So now we will go into more details of the scheduler piece of it. So filters and weighing host. How does the scheduler actually makes the decisions? So so if you see in this figure, let's say we had 6 hypervisors in our deployment. So we had host 1, host 2, host 3, and so on till host 6 in our deployment. So whenever a request comes in, depending on whatever filters are set. So filters is basically nothing but a key value pair, and there is a configuration entity named scheduler underscore filters in nova.conf, which will tell the list of filters a particular Nova scheduler will go through. So I will go through most of the filters in my next slide. But let's say we had just three filters for now: the RAM filter, the disk filter, and the CPU filter. And important thing to note here is the filters are evaluated in the order left to right. That means if I have placed RAM filter first, it will be it will it will be applied first, and it will just it will classify host which match the particular criteria imposed by the RAM filter. So let's say RAM filter imposes a criteria that give me only a list of hosts which have more than 70% of RAM free. So RAM filter will go through the list of hosts and only segregate those hosts which have 70% or more amount of RAM free. Then that list will pass to the next filter, which is our disk filter. Then disk filter might have some criteria, give me only those hosts which have 50% of disk free. So let's say out of 6, 4 were shortlisted by RAM filter. Then disk filter applies to those 4 hosts, and it says, okay, only 3 hosts are eligible for my disk are eligible. Now then CPU filter applies to those remaining 3 hosts, and let's say only one or all the 3 are eligible. Then at the end of the filtering, we have these 4 hosts: host 1, host 3, host 5, and host 6 available. Then weighing is applied. So weighing is nothing but how I sort these 4 entities, which is host 1, host 3, host 5, and host 6, in an order that I know which is the most optimal one. So amongst this list, we see that host 5 comes to the top. And there is a configuration variable again in nova.conf which says scheduler host subset size. So in our case, scheduler host subset size is 1, which means return that many number of hosts to the Nova scheduler, saying that, okay, right now host 5, so our subset size is 1, so just return host 5 to the Nova scheduler, that host 5 is the most optimal one for you, and you should proceed ahead with scheduling an instance on this particular host. So I hope this is clear. And we have a default filter list. So few things to note here are the default filter list and the host subset size, and how the filtering works. And the filtering works in left to right order given a filter. So the usual pattern that to be followed is put the filter that churns out maximum or that removes maximum number of hosts in the first, so that you don't have to do the process of filtering like like you remove maximum chunks of host in the first iteration itself, so that the upcoming filters will have to work on a subset of the number of hosts. So again, so one more important module to look inside the Nova Scheduler code base is the host manager piece. So what the host manager does is it basically makes a call to the compute nodes table in the NovaDB, which has an up-to-date information of all the resources and what their current state is. Let's say CPU usage is 50%, disk usage is 70%, and it will go through all that list. And first of all, what it will do, the host manager, is check whether the Nova compute service is running on those particular hosts. So let's say out of these 6 hosts, Nova compute service was down on host 2, then it doesn't make any sense to go or choose that host 2 for scheduling, because Nova compute process is the one which will trigger the basically the creation of an instance. So if Nova compute process itself, inside Nova compute, it will trigger the LXC, the libvirt part of it, and all those depending on your configuration and environment. But if Nova compute itself is not running, then it doesn't make any sense to pick up that host. So it will first check up on which all hosts the compute process is running. Then it will go and apply basically all the filters that are configured as part of your environment. So I hope this is clear. And let's go to the next slide and go through the list of filters. So filters, so there are few filters like core filter, aggregate core filter. So we, as a common, as someone who is getting introduced to OpenStack for the first time, so there is this concept of aggregate in OpenStack, which is nothing but a logical grouping of hypervisors. So let's say you want to group a set of hypervisors depending on their location. You want to group a certain set of hypervisors depending on a certain rack they belong to. So an aggregate is something that is only visible to your administrator, and a concept which is much more broader and is which is also logical is called as availability zone, and which is available to the users. So user has the ability to specify which particular availability zone instance should boot in, and that availability zone will map to some aggregate internally. So user is not aware of what aggregate a host is part of, or a compute node or a hypervisor is part of, but there is an internal mapping or a key value pair maintained inside an aggregate, which says that, okay, a list of host 1, 2, 3 are part of aggregate 1, which might be part of availability zone 1. So accordingly. So if we have core filter, we'll also have an aggregate core filter, because aggregate core filter applies to a grouping of hosts. RAM filter, similarly, we have aggregate RAM filter, and disk filter, we have aggregate disk filter. And that way you can apply it to a group of compute. So all these attributes, that is RAM allocation ratio, CPU allocation ratio, disk allocation ratio, are very useful when someone plans to overcommit their resources. And overcommit is very important when you want to meet the incoming demand with with whatever limited set of resources you have. And so these features are really important. So these are the basic set of filters. So in my example, as I mentioned, I just went through these four filters, that this three filters: RAM filter, disk filter, and IOPS filter. So if we can go to the next slide, please. Are you able to hear me clearly? So, okay. So I think the voice is clear now. So let's move on to the next set of filters. So I've grouped them as affinity filters. What affinity means is, like, given a particular request, we would like to schedule it on a particular host. So it's not always that we are concerned about overcommit, but let's say some rack goes down, or there is some power supply issue. So we would like host to go on a particular rack or a particular hypervisor, and if these criteria are specified, affinity that, okay, boot, let's say boot an instance, let's say you booted an instance which went on hypervisor 1. So we want an affinity that boot another instance which is closer to instance 1. So that means it will automatically pick up a host, that is host 1, on which instance 1 was initially booted on. So that is same host filter. Boot an instance on the same host on which a previous instance was booted on. Instance or VM. Instance and VM means the same thing. So instance is basically an abstraction. It can mean a VM instance or VM instance or a container instance. But right now, for this talk, we will specifically talk about VM instances, that is the virtual machine instances. So server group affinity filter, server group anti-affinity filter. So similarly, we have like simple CIDR affinity filter. And again, different host filter means if you have booted a VM instance on host 1, don't boot an VM instance on host 1. Boot it on some other host other than host 1. So host 1 might be having some problem, that disk corruption or something, and we will be in a process of evacuating VMs from that instance. By evacuating, you mean like, or like moving VMs which were running on that particular hypervisor to a new hypervisor. And this way, since we are setting a policy here that don't and making decisions at the scheduler level itself, we are in a process, or the user or the admin is in a process to much more fine grain or tune or have a control of where his instance will be placed. And this is most of the scheduling entities out there, like even Kubernetes. Google Kubernetes does the same thing, which gives more control to the user, as in where they want to place their containers, or in our case, where we want to place our VM instances. And that is very good in my opinion. So let's move to the next slide. So the topology filters. So there are few filters like aggregate image properties isolation. So let's say one of the cloud deployment just provides Linux images, but there might be a requirement going ahead that people might ask for Windows images. So what aggregate image property isolation filter does is it allows you to create an aggregate, set some add some host in that aggregate, and set some metadata on that aggregate, which will allow and set some metadata on that aggregate which matches Windows image. So Windows image might have some metadata, let's say key foo is equal to value 1, and then the aggregate also has foo and value 1. So the Windows image will match, will know that I have whenever the scheduler boots and it has this filter set, which is aggregate image isolation filter, it will know that given a Windows image, it has only to go to this particular Windows aggregate, and it can't go or boot in any of the Linux aggregate. So this grouping of hosts at an aggregate level helps, because you set the property at the aggregate level, and let's say tomorrow you want to boot a free BSD VM, and you have a dedicated set of hypervisors for that. Aggregate image property isolation helps you to achieve that without making any additional changes to your scheduler workflow. These filters act as a plugin which basically runs on demand when they are enabled. So, and you can run, so these plugins can work and can help to, hello, can help to schedule instances on those particular aggregates. So, so now the next is the availability zone filter, which can be used for like booting instance in a particular availability zone. So let's move on to the next slide. So we have other bunch of related filters. So we can go through others, and compute capability filters. So given a particular capability, it matches, the scheduler matches that what capability is specified in the extra specs, and will try to boot accordingly on those particular hosts. Then we have the compute filter, which is a very important filter, which basically checks whether a particular service is running or not. And that is a predominant, or that is a first criteria that is the scheduler uses before picking a particular host. And compute filter also goes into the concept of service groups, and seeing, which is nothing but a grouping of services, and then seeing whether all the services belonging to a particular group are up or not. So grouping is like Noah Compute will have a set of all the hypervisors and Noah Compute service running on them, and then it will make the is up call to check whether the service is actually running or not. So we will have JSON filter, image properties filter, depending on particular architecture, boot a VM on this particular architecture. And we have number of aggregate number instance filter, so which will restrict maximum number of instances on a particular hypervisor. So accordingly, this plugin based architecture helps to turn on and turn off a feature, and basically, depending on your environment, what your needs are, what your requirement is, you are ready to go as and when needed. And it's one of the good thing to note is it's one of the main reason for slowdown as well. So you need to be pretty sure about what you are doing in the filters, and the filter logic need to be written in a way that it is it can do minimal comparisons and return in an optimal way. Otherwise, there have been instances previously where it is not an order of one or order of one operation, but depending on if you have more number of hypervisors in your deployment, it will take that much number of time. Let's say you have order of n number of hypervisors, so request might take n seconds, and if you have like n squared number of hypervisors, it might take n squared number of times. So you had to be very cautious and very smart in writing these filters and going through them, so that you know that your scheduling is not slowed down by the problems in the filter. Okay, let's move to the next slide. So let's move to the next slide. So this weighing is the next step after the filtering is done. So in our previous slide, we saw that out of 6 hosts, four hosts were selected by the filtering logic, and now weighing, mostly the weighing is done based on these three factors: IOPS, weight, matrix weight, or RAM weight. And the RAM weight is the default one. So at the end of the filtering, weighing will decide that which host has maximum amount of RAM available and then schedule the VM there. So which is like RAM weight can be set as zero point 0.5, whatever host has maximum amount of RAM available, schedule me there. So, and the matrix where is something that can be used more for getting the actual utilization. So right now, mostly we have just the CPU metrics available, but I have written I proposed a spec which also takes into consideration the disk and memory metrics, and it is still under progress. And hopefully, once that is there, we can have more of logic around that, but it's still under review. So by default, right now, the thing to remember here is the RAM weight weight that is applied by default. So let's move on to the next slide, please. So quota, why quotas? So first of all, in any given deployment, there is a need for efficient use of resources, and there is a limitation on resource consumption. So first of all, like any deployment that we have is has a limited number of servers, and everything has a cost associated with it. So studies have shown that only like 61%, like 29% of the resources are consumed, and 71% is not consumed optimally. So these are some studies conducted by various research organizations, and so it clearly shows that the resources are not optimally utilized. And also, as an admin, you want to place restriction on the number of resources consumed. You don't want to end up in a starvation kind of a scenario where only single user, may it be a valid user or a malicious user, consumes all of your resources in your cloud, and the other resources, other users or other consumers of the cloud are starved. So Quota imposes these restrictions at a project level. So project or a tenant is nothing but a grouping of users in a cloud. So uh, so given a particular user or a project, there is a limit imposed on the number of physical resources to be consumed. Like let's say Noah, there is like how many CPUs you can consume, how many maximum amount of RAM you can consume, how many number of instances you can create, how many number of uh, RAM you are allowed to consume, how much amount of vCPUs, that is the virtual CPUs, you are allowed to consume. So the current state of OpenStack is that every project, that is Noah, Cinder, Magnum, which is container as a service, Neutron, network as a service, has a set of resources against which quota must be imposed to guarantee fairness. So Noah has CPU, vCPU, RAM, disk, number of instances. Cinder has number of volumes, number of snapshot, how much amount of disk. Magnum has number of bays to be created. Neutron might have number of ports and etc. So, there are various admin CLIs provided to get the current usages of the resources. So, right now the quota is imposed on a flat namespace. What I mean by flat namespace is you just have a single cloud admin user which manages projects. So let's say you have a cloud admin user which manages a project called as mail. You have a cloud admin user which manages project called as maps. You have cloud admin user which manages project called as YouTube. So if the YouTube project goes out of quota, he has to contact the cloud admin user. If the maps admin user goes out of quota, he has to contact the cloud admin user. If the Gmail or the mail admin goes out of quota, he has to contact the cloud admin user. So which is not a scalable system, because in real life, the namespace or the project organization is not flat, but it is more hierarchical in nature. And that's why we need nested quota. So first of all, we got the idea of why quota is needed, because it imposes a restriction and guarantees fairness of resources amongst the user of a particular project. And now we see more real life example that the way the projects are structured in real life is more hierarchical. So there is a need for nested quota, which basically imposes quota in this hierarchical structure, not in a flat structure, but in a hierarchical structure. So that ways it helps that the single cloud administrator, it releases the single cloud administrator from the burden of managing quotas for all the sub projects that he's managing, the maps, the YouTube or the mail, and it delegates the responsibility to those respective administrator of those projects. That is, cloud administrator of maps will take responsibility of quota for maps. YouTube will take cloud administrator for YouTube will take responsibility of quotas for his respective project. And if they run out of that, then they will talk to the uh, the main cloud administrator who is managing the entire cloud. So there has been effort, and Cinder was the first project to accept nested quota, and I happen to be the developer who had this idea and implemented it in Cinder. So the way it works is we keep track of the usage, that is the available resource, the used resource, and the free resource for every particular project. And in this hierarchy, before updating, before consuming, let's say we had this uh, hierarchy of the cloud administrator and YouTube. So in that case, before consuming any resource in YouTube, we will make sure that YouTube has enough free capacity for the resources, and then only allow consumption from YouTube. If YouTube runs out of capacity, then first YouTube administrator will invoke a call to the main cloud administrator, and then he will service the request or add more quota to YouTube, and then YouTube will be able to serve the request. So also, a few points to note here is that if you do concurrent boots in OpenStack at present, like you do 10 boots and 10 delete, or 5 deletes and 15 boots and 10 deletes, or any this permutation combination, the quota infrastructure right now is broken in a way that it cannot handle concurrent requests, and it might show you abrupt usage records. So there is a CLI such as NOAA quota usage, which gives details, or NOAA absolute limits, which will give you details of, from the CLI perspective, how much is used and how much is set for my particular project. So there are anomalies there about the actual usage and actual consumption. So that might lead from prohibition of provisioning of new instances, because because OpenStack's OpenStack completely relies on these usage patterns or this consumption statistics to give a detail of what is it allowed to boot a new instance or not. So that might block you from provisioning new instances. So that can be a serious threat, considering uh, you might run into problems that you won't be able to provision new instances. So in where you might need to provision in a serious need of provisioning new instances on demand. So as a result of that, we thought of having a common library and proposed this library called as delimiter, or it is just an entity right now. We are still working on making it, whether to call it a service or a library for quota management and enforcement across projects, because the goal of this library is to have a common platform or a common quota library, which will be common for Cinder, Magnum, Noah, Neutron, and it can also be helpful for new upcoming projects, which let's say Glance or Project Foo, who want to adopt to this quota infrastructure and do not want to reinvent the wheel and start investing resources, time, people in getting the quota infrastructure set up, because it is a complex piece of code, and getting it up and running might take like 6 to 1 month, 1 year of time. So, and also we can add the features on demand to this new quota library. So I would like you to visit this spec, that the link for that is proposed here, and also propose us new suggestions and inputs, and help us to make the quota infrastructure better, and help everyone accordingly, and we can solve this common concurrency problem that the quota infrastructure has, uh, the the ability to add new features. Like there are many new features that are needed by operators, like quota by AZ, quota by availability zone, quota by flavor. So all these things can be moved much quicker if we have a separate entity. And quota is a very complex piece, and if we have it at a common place, in my opinion, it can move quicker, and we can help and grow as a community. So next slide, please. So, so in the next slide, so yeah, that's it I had for my talk, and I have my email. I have like my email ID, and there in the slides, and if not, I'm reachable on IRC. My username is Vilobh. So I think I don't. So feel free to reach me on IRC, and my username is Vilobh, and if you have any questions regarding scheduling and quota, and would like to contribute, I'm I'm more than reachable and more than happy to help. And yeah, that's it from my end. Feel free to ask any questions if you have. Hello.
Hey, Vilobh.
Yeah. Hi.
Um, Thank you so much for the talk. Do we have any questions? So we have a question here. Can you briefly describe us what the scalability is? What kind of scale can we apply to this quota management?
So
And what
right
is the
now,
objective
right.
of this library?
Yeah. So right now, with the existing way it has been implemented, even if you try to boot, let's say, more than 10 instances in a concurrent fashion, you are bound to run into problems. And there have been bugs opened on Launchpad. I can provide a link for you. Even the delimiter spec that I proposed has the details of previous evaluation of what all problems are there in the existing quota infrastructure. So I would strongly recommend you to go through that. But even if you try to boot 10 concurrent boots, you are bound to see a problem in the usage, the actual quota usage, and the actual usage on the compute. So that is not in sync. So the compute might see a different picture, and the quota infrastructure might see a different picture, which doesn't help in provisioning new instances. So even though there might be enough capacity available on the compute, but if the quota infrastructure doesn't see it, it won't allow you to provision new instances. Does that answer your question? So as a result, to prove this, we have a plan, as like we can have a test suite or a functional test which will basically concurrently boot more number of instances, may be fake instances or more number of actual instances, and it will basically prove this point. And there have been bug opened, as I mentioned. I can point you to that. And yeah, does that answer your question? Hello.
So we have a follow-up question here.
Yeah, sure.
Magnum. Right. Sounds good. That's a great question. So the question is, uh, something like a Magnum service that's supporting containers can issue, builds of, order of hundreds to thousands. In that case, how do you scale this? So you gave an example of Nova where it was builds of minimum of 10, but
Right.
when it goes to that large extent, how do you actually manage that?
Yeah, sure. So Magnum, the interface for Magnum for provisioning is Heat. So Heat right now doesn't have the concept of quota. And so Magnum is, what Magnum does is it creates a bay. So bay has nodes, a set of nodes on which you create those containers. So so the nodes are created and those are provisioned by Heat. And Heat is basically actually talking to Nova and then consuming resources from Nova. So since Heat doesn't have a concept of quota as of now, there is no way to keep track of it. So that's a really great question, and right now there is no such what you can say a validator entity or an entity which will prevent Magnum for consuming most Magnum being at a more PASS layer, that is platform as a service, from consuming more number of resources from the infrastructure as a service, which is NOAA. So that gap needs to be built out, and in this common effort that we are talking about, we are going to plan according to that, and then see how we can come up with a common platform that will basically help to bridge that gap. But as of now in Magnum, so I've introduced quotas in Magnum recently. So a spec for that has been approved, and so right now we have limited it just to the number of entities that Magnum understands, which is Bay, and nodes and other resources that are consumed by Magnum is out of Magnum scope, because that is nothing that Magnum can control. So we have just limited it to nodes, just limited it to base, sorry. And we did bring up, I did bring up this point that how will we uh, address that, and we are under talks. We were under talks with Heat, and that time, like, we will plan to address this as part of the common library that we have proposed. So right now, the short answer to your question is the past layer right now, since Heat doesn't have the concept of quota, is not restricted to the number of resources it can consume from the IS layer. So it might end up consuming more than what is prescribed, but given a particular limit that is set in NOAA for that particular project, it can't go beyond that. Does that answer your question?
So there's a layer of Nova which is making it tougher.
Imagine the same concept for the filters
Right. Not yet, yes. Because it's the layer of Nova is which is making it more difficult for Magnum to go that fine grained and establish the scheduling management along with quota management for
Yeah,
that.
so Magnum's interface is Heat, and Heat will internally invoke NOAA. Yeah, that's a really interesting question, and that is something that we need to address, and that's a really nice question. Thanks for asking that.
Thank you. I guess that's it.
Sure.
So thank you for the great presentation and answering the good questions.
Yeah, I hope it was helpful, and please feel free to reach out to me
Yeah.
and uh, ask as many questions as you want, and I'll try to answer them um, as much as I can.
Yeah, that sounds good. So I think you're going to get a lot of questions because this is going to get published on YouTube.
Sure.
And although we had a a great a small net group which was talking about OpenStack a lot today.
Mhm.
But once people really get to pinpoint all the things that you have talked about and pause the YouTube video,
Mhm.
then you're going to see a lot of flurry of questions there.
Yeah, more than welcome. I'm more than welcome and happy to help.
Excellent.
Sure.
Thank you.
Thank you. Okay.
Bye.
Bye bye.